Okay, so where do I want to start from? I want to tell you that the Biot Savart is the equivalent of Coulomb's law for magnetism. So just like Coulomb's law was the general law that you'd use to solve for the electric field or the force, whichever one you'd like, in a region from some kind of charge distribution. The Biot Savart is the equivalent in the magnetic world. So you basically find the magnetic field from some kind of current distribution. And it's general. It will literally handle anything. The problem with it, though, as you will see, it tends to get very cumbersome, very complicated. The integrals get to get very disgusting. And in general, it's not very friendly of a law. So later on, probably this week that's coming up for you, you're going to do Ampere's law. And Ampere's law is going to be the brother of Gauss's law for magnetism. Okay, it's going to be completely different in terms of what you use for it, but you see their structure again. Like there's similarities, there's equivalence for the magnetic and the electric world. And then, if you were studying physics in third year, eventually they'd merge the two worlds together into electromagnetism. But for now, for you, you have electrostatics and magnetism as separate entities. However, they're one of the same thing. And all that differs really is the reference frame. If you were to put yourself, for example, in the frame of the current down a wire, you'd see electric forces because you would see stationary charges. But if you see the wire from afar, you see a current. And so you see magnetic forces instead. Not going to get too much into why, how to prove that, but you can. You can prove that. And we do that as an exercise for Physics 342. Now, getting into the meat of things, what does the law say and how do you use it? So I've given you here in the note, basically a wire. The white squiggle here is a wire. And I want you to understand there's electrons flowing down this wire. However, the individual electrons, they move down the wire very slowly. The drift velocity, if you've heard of like wires, is like tiny. So it's not, again, the individual electrons that are causing this current. It's the mass movement of the electrons that's causing the current. And I want you to think of current as a quantity that the entire wire shares, like the entire wire here, anywhere you measure it right now, if you measure it here or here or here, it shares this current. It's a property that is wire, exclusive. Why is that? Because current measures flow. It doesn't measure absolute electrons. In a particular moment, maybe there's like a clump of electrons here and maybe not so many over here, but overall, the current doesn't look at that, okay? It doesn't look at the micro. I just want to get your attention to the macro. It looks at the wires, like overall. The micro stuff, you don't look at when you're doing current. And another thing I want to get you prepared for, because I don't know how far they're going to push the Biot Savart law. They could ask you questions on current densities that are not 1D. For example, you might have to use surface current density or even volume current density. I've never seen these in the curriculum of 106 before. I've seen them in Physics 342, but you never know. Considering what they've dumped on the midterm this year for you, I'm very, very open-minded. So I want you to think of current in a very specific way. Think again of an electron over here, just moving down the wire. His buddies are following behind. What you're measuring, it's like you take a scissors right now, pair of scissors, snip the wire, and ask right now, how many of these electrons are passing by this cross section that I made every single second? That is literally what current measures. So it measures the flow of these electrons through that cross section that you made. We're going to talk about 2D and 3D current distributions when you do Ampere's law, guaranteed. But for now, get this picture into your head, the toll booth picture, that the electrons pass by and you measure how many of them are passing by every second. That's the idea of current. In fact, the definition of current, you've probably seen it in your circuits course, is dq over dt. It literally is what I'm telling you, change of charge per unit time. How many electrons per unit time pass that cross section? Okay, so we got the wire in. Let's explain what the law says here. What is this guy? This guy's a constant called the electric, again, permeability now, okay? Not permittivity. Permittivity is the epsilon naught. So it's the permeability. What are the units again? Or rather the value in SI units? 4 pi times 10 to the negative 7 henries per, you might be catching me lacking here. It's henries per something. But you can find that very easily on Wikipedia. Like in SI units, this pops up immediately. That's what we put in here, unless we're told that the material that we're using is magnetic, right? It's like the equivalent of dielectrics in the magnetic world. So if you wrap a solenoid, for example, around, let's say, air versus if you wrap it around a magnetic cylinder, the mu is going to be different between the two. For the air, it's going to be mu naught, but for the magnetic cylinder that you wrap it around, it's going to be some other mu. We're going to talk about that if we encounter it. That's what typically goes in here. Okay, well, we talked about this guy again, and the 4 pi is just a constant here to get rid, I guess, here in the Biot Savart law of the 4 pi that the mu naught carries. Okay, these just cancel. And now inside is the interesting bit, okay? You got a cross product. You got this DL guy who is a vector, I remind, crossed here with this curly R guy. Usually I make this blue on my diagrams. So what does this mean? What are the roles of these guys? Okay, one thing at a time. Let's erase some of the stuff here, and I will redraw it. So usually you will be asked to find the magnetic field with a Biot Savart law at a specific point, okay? And for argument's sake, maybe that point right now is right there. So what does the R, first of all, do? It always connects your point of interest to one of the contributors of magnetic field. So when you look at your wire, you're going to want to break it, of course, into segments. For example, here, a segment could look like this. This could be right now a DL. And it will be a DL if we give it a direction as well. So let's say right now, this guy here, this segment that we're breaking, if one node cooperates, that is. So let's put a little segment here that looks like that. That is our DL right now. If you notice something about DL, is that it's following the direction of the current. In fact, it is literally the direction of the current. Sometimes you might see the Biot Savart law if someone that is very outcast is writing it. You might see the Biot Savart law written like this, by the way. This also happens because literally the DL is the direction of I. And as with any vector, you can express the I as a magnitude and a direction. So what we've done is we've basically split the vector up into like its magnitude and its direction. And that's why you see the magnitude pop out here and then the direction come in there. But it's literally the same thing. This is the direction of I. I need to let you know. So we understand that. And at the same time, it considers a very small chunk of your wire right there. So the R vector now, the big blue here, these are related. We'll talk about them in a second. But the R vector itself, what it does is it connects your considered here DL to the actual point of interest. That's what you do. And as the integral moves along, you basically have the r vector do this. As you integrate around the wire, you have the r vector do this, right? And you consider all the DLs that make up the wire and their respective magnetic field that they contribute. That's how you do the integration. The r just moves around. So we always take a snapshot and work things out, of course. So this is the r vector right now. And how do you get here the r unit vector? Well, again, you use your 115 skills and you remember that this is just going to be the full vector divided by its magnitude. That's it. So basically, you have a vector for this guy that literally points like this. It's a unit vector. So it points in the direction of r, but has unit length right now. And that is it. So that's what the law is, and that's how it works. So there are a few, intricacies that I want to let you know immediately. Sometimes you know the direction of the magnetic field. Like you'll see problems where by symmetry, you will immediately be like, the magnetic field goes straight this way. In some other times, it'll be like, I don't know what the heck is going to happen. I have no idea. So for the times that you do not know what the magnetic field will do, you use the law as is. As you see it right now in the picture, this integral is what you need to do. However, when you do know what the direction is, you can take a bit of a shortcut. Because again, calculating this cross product is time consuming. And if we could get away a little bit with it, we would rather do that. So only we use this full equation when we don't know the direction of the magnetic field and we got to do the actual cross product. Like the right-hand rule, for example, won't help us. We don't know exactly what to do. So we use, the actual full law. What's the shortcut? Well, sometimes, again, if we know the direction, we can do this. We can take the size of this cross product. And what this saves you is the pain of doing the cross product itself, right? Because you can open this up. If you remember, again, from 115 or ECE 105, you can open this up like this, right? So all you need to do is figure out what your DL is, figure out what the size of the unit vector is. Well, that's just 1, right? So that even goes away, and you're left with this. And the sine theta here is the angle between, like theta is considering the angle between these two guys. So yes, that's a lot faster than having to express DL as a vector, express r hat as a vector, do the cross product between them. You know what I mean, right? So you're going to see this version being used a lot when we have symmetry. I guarantee you. This is, again, something that we use for symmetry. And this is something that we use when there's no symmetry, or at least we haven't spotted the symmetry, naively. Okay. And as you notice again that the bottom one doesn't have a vector sign here. Obviously, there are no vectors in here, right? There's no vector remaining. So the bottom one is just talking about the size of the magnetic field, because that's what you're chasing after. I said you already know the direction, right? If you're doing symmetry, you're already knowing where the magnetic field's going to go. So you're going to slap that direction at the end on the magnetic field strength. But if you didn't know anything about the direction, you'll go with a full version, right? You'll go the longer way. So we'll see both of them in action. Don't you worry. Now, a little trick to apply the right-hand rule, okay? Because you might not even remember how to do the right-hand rule. Suppose, again, you want to do DL crossed with R hat, and you've got your DL right now pointing this way. Let's say your R hat points this way. How do you do this cross product? I will leave the question. If someone wants to tell me right now how to arrange my fingers, I will leave the question open. Who wants to jump in and tell me how to arrange the fingers to do this cross product? Just to see if you know how to do it. Where does my thumb go? Where does my index finger go?
Yeah, thumb points up, index points out.
Okay, so
and
yeah,
and also middle finger points perpendicular to index.
Good. So again, here in this case, the order that we've written this is important. The first guy that you see here is your thumb. So your thumb is going to be pointing out. And then the second guy is going to be your index finger. So you're going to see this reverse in the camera. Don't follow me. Okay, follow the diagram. So you're going to be pointing to the right for the R hat. And then your middle finger is going to tell you where the actual cross product points. In this case, it's inside the screen, toward the screen right now. Okay, and we've got symbols for that. Just to remind you, this symbol means out of the screen. This symbol here means into, okay? So again, keep that in mind. Now, what if I flip the direction? Well, if you flip the direction, all that's going to change is you're going to get the opposite result. If you remember from Math 115, when we flip directions, we basically get a negative sign for our cross product. This is a property again from, when you're doing cross products in 115. Okay, how about if the cross product here is not obvious? Let's talk about that for a second. What if I had DL to be going like this right now, and I had my R going like this right now? What do I do now if I'm faced with this situation? If you try to apply the right hand rule, you're not going to get anything, right? You're not going to get a result. What you need to do here, okay, is you need to break one of the vectors into components. You need to project one vector onto the other one, and then you're only going to do the cross product for the components that are perpendicular. And if you don't understand here what this means, let me again do a nice diagram for you. Here's what you need to do. Let's say you want to break down the R vector. You see that it has a component that goes like this right now. Let's say this is the R hat perpendicular, and then it has a component that goes like this, the R hat parallel. Obviously, the R hat parallel is not going to contribute anything. Cross products between parallel vectors are 0. So this guy might as well not exist right now for our purposes. So in order to do the cross product now, you need to use this guy only. And you do it as you would. So your thumb again would be along DL, but this time your index finger would be along R perpendicular. Okay. I'm just letting you, Kelly, in. I think you're joining from another device. I'm just letting that in. So yeah, DL this time along the thumb and R perpendicular along the index finger, giving you again a result into the page yet again. So that's how you do slanted vector cross products, like when they're not exactly perpendicular, right? Because this happens a lot in magnetism. So got to let you know that you need to break one of the two vectors, you need to project it into the other one and pick only the perpendicular component to do the cross product with. I'm sure you have found yourselves wondering, like, how do I rotate my hand, to go with the R hat right now? It makes no sense. I can't really do it. Like my fingers, how am I supposed to put them? Now you know. Okay. That's all I had for the note. So now I want to get right into problems, right? Because obviously we don't have that much time. And we have quite a bit of a topic today. Here's problem 1, okay, that we want to think about right now. So this is the simpler version of a problem that we're going to see. Straight wires here completing a circuit like this. The current, again, let's draw this out 1 second. Let's draw it with our own diagram. So I'm going to do that right now. And I'm going to erase here like that. Just, it's like a curved wire segment, but it's not like, it's actually like not even. Let me just do this because I know this is going to suck as a diagram if I don't do that. I'll just steal the left circle right now and I'll just make it bigger. That's what I'm going to do. Something like this. Yeah. Fair. Okay. So I'm going to line them up like this. And we're going to put our point of interest here. Going to put our point of interest at the bottom, it seems like. So it needs to line up. It needs to line up. How did I end up messing this up? Okay. Why don't I just use the diagram they've provided me, instead of wasting the time to draw it? It's just that OneNote really reacts when you draw on pictures. It doesn't like that. That's okay. Let's take a look over here, how the magnetic field is going to play out from each of the directions here. This is our first job when we look at this. We see the current going around like this. Okay. So this means that our DLs are going to point in the same direction. When we attack the problem, our DLs are going to point in the direction of the current. So I'm going to pick one here, one here, maybe one here, and then one here. And automatically you see that I've broken the problem into 4 regions, right? Like we can even label them 1, 2, 3, and 4. And so, looking at these regions, not all of them are going to register magnetic field at point P. They're not all going to contribute. I'll explain why. You can see here the point P right now. Let's say I want to work with region 1 over here. And I'm going to highlight what region 1 entails. This is region 1. Why did I pick this region? What makes me, again, work on this as a separate region from the others? I know that it looks to you that it's separate, like intuitively, but what exactly is the reason that I'm separating it? Let's see what the reason is. I want to ask here, let's see, who do I got? Who's going to be my victim? Kelly, what coordinates should I be working in this problem, you think? Like Cartesian, polars? What do you think?
Polar.
And polar coordinates here involve an R and a phi. So while I'm still on Kelly, I want Kelly to riddle me this. Kelly, if I move along this direction, I'm highlighting right now. If I move along this direction, and I'll put your coordinate system here, just want you to see it better. Okay. Here's like my y-axis right now, and here's like my x. I just want to know right now, Kelly, if I move in this direction right now, what variable out of these two is changing? Is it phi or is it r? Or both if I move along this direction?
Just R.
Just r. Now, take a look at this, Kelly, while I'm still on you. What if I move, so get rid of this box. Look at my green arrow. What if I move along region 2 here? What variable changes now only?
Phi.
Phi. And then again over here, if I move from the back of region 3 to the front.
R.
Yeah. And then finally again over here.
Phi.
So you guys see something special about what we just did? I always was changing one variable. And that's what drove me to break the problem into 4 parts, because each one was changing one unique variable at a time. Because if I had considered region 1 and 2 together, I would be moving along R here, and then phi, it would be messy and not really, again, even solvable. So I split it up based on one variable at a time. How do I move while changing only one variable at a time? That's how I got the 4 regions. Okay, so besides intuition, there was actually a legit reason to do the breakdown. Now let's move forward. Let's see what else is going on here. You got the coordinate system in here. Just want to put it a little bit below, because now I'm going to start using my R vector. Here comes the R vector. We said what the R vector does, right? It always points from DL toward the point of interest. So there it is. Okay. So slowly, for region 1, okay, let's consider what this R vector is going to look like. Well, I see right now that this R vector, all it's going to do is literally just point in the negative R direction. That's where it's pointing. Like, it's pointing toward the origin of a polar coordinate system. That's all it will do, literally, throughout the process here. So it's going to have some size that will vary. It's not going to be A. It's not going to be the B that you see here. It's going to be something between A and B as I do the integration, right? So, you know, I don't know exactly how big it's going to be when it hits the L. I'm going to let it be a variable. So R, the vector, is going to be some size, but it's pointing in the negative R direction in the polar coordinates. I don't know the size. I really don't. Now watch this. What is DL doing? How can we describe DL right now? That's our next job. DL, again, let's see here. It will have some size. That's how we write vectors, magnitude. What would you say its direction is? Let's ask here, hold on. Leah. Let's ask Leah. In a polar coordinate system, where is this guy pointing right now? Okay. What do we know? Or what do we see? Just to help you out a little bit, points away from the origin in a polar coordinate system. R, yes. Okay. All right, so it's R, positive R this time. I just want to remind you what the Biot Savart law says. It says mu naught I over 4 pi, the integral of DL crossed with R hat over R squared. And I don't know about you, but when we do the cross product between two vectors right now that are literally pointing in the same direction, yell it out. That what should we get here if we do that? Yell it out to me. If they're parallel or anti-parallel, and we do the cross product right now, let me highlight here the directions. What should we get? Who wants to tell me? This is literally the cross product between R and R hat right now. Literally, these are the same vector. What did we just say on the note? If two vectors are parallel and you try to take their cross product, what happens? Maybe Bogdan can help me?
Sorry, can you repeat the question?
So what happens if we take the cross product between two parallel vectors? Parallel.
Oh,
Not
would just be 1?
That would be the dot product. If these were being dotted, that would have given us 1. But if they're cross-producted, it gives us
Or it'll just be 0.
0. What does that tell you, Bogdan, about the contribution of this segment to the magnetic field at P?
There's a contribution, doesn't do anything.
There isn't a contribution, okay? So B is 0 from that side. Okay. Can anybody, out of all of you, guess another side that's not going to give a contribution right now for the same reasons? So we said 1, 0. What other side could possibly not give a contribution?
Side 3?
Uh-huh. The only difference with side 3 would be the DL is pointing toward the origin. So it's in the negative R hat direction. The R, still the same. So all that would be different for side 3, this would be a negative R hat. But still, the cross product doesn't care. It sees 2 R hats, it will yield 0. So 3, again, B is equal to 0 for the same reason. All right, so we got rid of these, and we still have to go and do the others. So let's look at maybe side 2, right there. Okay. Now, I want Kelly here to tell me, how big do you think this vector R stays? You told me that only phi changes as I move along side 2. Only phi. That means that R is constant. What do you see on the diagram about the size of R right now? How big is R?
B.
B, exactly. So we know right now that the R vector, Kelly, will point, as you can see, still in the negative R direction, but its size is going to be B. We know what the size is forever. Okay, I want Natalie to prepare here, okay, for the next question. So, Natalie, I want to know what DL is. I'm in polar coordinates, okay, and I want to know how big DL is. I will help you out a little bit by doing something on the diagram as usual. I just want you to tell me here using maybe the arc length formula, something like that. How big should this DL be in terms of this little angle that I opened up and the R over here? RD phi. All right. So specifically for us, the R again is B. Okay, it stays constant, but you're very correct. Okay, so DL, the size of it, we can do it as a vector actually. So the size of DL is R, curly R, which we said is going to be B, and then times d phi. The direction it's moving right now, this is defined as the positive phi direction if you're going counterclockwise. So this is positive phi. There you go. Okay, so let's think for a second. I'm going to delete that bit here. Let's think for a second how we can deal with this right now. We will need to take the cross product between them. We know that. Okay, so I'm going to go ahead and prepare it like this. But
Wait, sorry.
yeah.
I don't get why, like, for R, why is it negative but not positive?
The R?
Yeah.
Oh, because again, if this R vector is pointing toward the origin. If it was positive, it would be pointing the other way around. It would be going like this. So positive R direction is away from the origin in polar coordinates.
But why in this diagram is towards the origin?
Because the R vector, its job is to connect the point of interest, the element, and the point of interest, and it points from the element to the point of interest. That's where you want to find the magnetic field right there.
Okay.
All right. So that's why we have it directed like this, and it's in the negative R. Now, the next step is to take the cross product. And even though you can go and actually do it by hand, I suggest using your own hand to do this, okay? Take a look again at what we can do here. Whenever you're doing the Biot Savart law, spoiler alert, because cross products exist, you're not going to be in 2D. I guarantee you, you're never going to be in 2D. You're going to be in 3D. Cross products are not defined for 2D. That concept doesn't exist. So why don't we come in here and say, what's the 3D version of polar coordinates? That's cylindrical, right? You have like the plane of the polar coordinates, and then you extend it in the Z direction. That's cylindrical that we're going to have to use. Okay, so where should we make Z point in this diagram? Well, it would have to be perpendicular to R and phi. Where does R and phi point? R points like this. We can think about it in a single snapshot that it points like this. Phi points like this. You know, if you take them at a different location, they will point differently. But the point is, they're both on this plane right now. So that means Z for us should be either outside the page or inside the page. And we got to choose. Typically, what I do is I let the outside the page, this is outside the page, be the plus Z, and the inside the page to be the negative Z direction. And then I merge it together with my polar coordinates here to give a complete picture. That's, again, my cylindrical coordinate system projected in the plane, I guess. That's what's happening right now. So I put that in to show you that the cross products here that we're going to take, they're going to give us some kind of Z. Let's see what I mean here. So we want to do DL crossed with R right now. I understand, obviously, that this guy, the unit vector of R, obviously is going to be directed along its parent here. Like they will look like this, right? Like they're you know, the parent is the big guy and the unit vector is the small guy, the orange. Fair enough. So I want to take the cross product between these two. Take your fingers. I want someone to actually tell me. I want Leah to try this out. Okay. Thumb along DL. Okay. Where we are on the diagram. I can zoom in so you can put it again. You can put your fingers very well on the screen. Thumb along DL. Index along R. Where does the middle finger point right now? Toward you or away from you? Those are the two options. Let me know. Toward or away? If you're unsure, you can also tell me that too. You say away. All right. You're saying away. So again, thumb along here, along the DL. Don't follow me because I'm mirrored on the camera. Along DL, and then to the left is your R hat, roughly. And then your middle finger, I don't know if you can see on the screen, that middle finger is pointing toward my face, right here. It's coming toward my face. So it would be toward me this time around. Toward me is this guy. Okay, all right. So what does that mean? Can I use this kind of right-hand rule to find the direction of the magnetic field? You might be thinking yes. However, it's actually not true. You have a wire in your hands. In the magnetic field in a wire, what it does, you've probably been told this, it circles around, right? It goes like this, above and below the actual wire. So when I look at point P, Okay, when I look at point P over here, one of these circles, again, one of the components of these circles is going to hit me right now. It's not going to be the part that goes below or above over here. It's going to be either the part that comes out of the page or goes into the page right now that's going to hit me. But I got to figure out on which side is the X and the dot. I got to figure out which side, again, the rings dip into the page or they come out of the page. I need a visual for you to see this because I'm sure you're probably confused. Okay. So I don't have a wire here, but I guess I can use something solid. Let's use a pen. Here's the wire. What I'm telling you is, okay, pretend that my eyes here, I'm going to try and line it up with the camera. My eyes are the point P. We're looking at this from a side view right now. And this is the wire that you're interested in. Its magnetic field, how does it look like? It looks like a loop, okay? It looks like this. You see it from a side view? That's what it looks like, a loop. Now, what is going to hit me when I make the loop bigger and bigger and bigger? What is going to hit me when I get to my eyes right now? It's going to be either the component here. If it's going up, that's what's going to hit me, or if it's going down. I'm not going to get hit by this or by that. I'm on the plane myself. Okay, I'm on the plane here. So again, I want you to see the plane with my hand. So that plane gets hit right now. Follow the direction of the loop here, okay? I want to show you. Follow the direction of the loop. This is my plane. Hold on, right there. This is my plane, my hand over here. I hope you can see that the intersection between my hand and the loop happens at 2 points, right there and right here. Those are the 2 points. There's no intersection happening here, 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 here. It's only, as you can see, here and here. And at those points, let's say the magnetic field was going this way right now, okay? If you're here, the magnetic field is hitting you into the page. You see that? Like that. And if you're over here, the magnetic field is hitting you like this, up right now when it intersects that plane. Those are the 2 options. You don't have other options. Okay? So think of point P belonging to a plane right now, the plane that the problem is written on. Okay? And you've got a bunch of loops that are coming in from that wire that are basically in the page. Like I wish I was in person. That would make a lot more sense if I was in person. But again, over here, those loops intersect the plane, as you can see, like this. Point P again could be over here or over here on the plane, anywhere on this plane. But no matter where point P is, I want you to see that the loop right now will intersect it at 2 points. And depending on the direction of the magnetic field right now, it's either going to be outside or inside the page. So again, my finger is going to point either up or down right now. Sorry, I kind of ruined the loop there. That's it. Either up or down. What you're seeing in the problem here, this is the side view. This is going to be really cool. This is the side view that I'm explaining to you. What you are seeing in the problem right now is this. That's what you're seeing right now in the problem. So you're seeing the loops from above, okay? But on the side view, they look like this. So that's, before I lose you, that's exactly what I'm trying to imitate over here. Where'd my pen go? I lost my pen. Besides my mind, I also lost my pen. 1 second, let me. Oh, there it is, okay. So before I lose you, you're looking at this. And the loops, now you can probably see what I'm talking about. The loops are going like this. Diving into the page maybe, or coming out of the page here and here. I gotta find though, which side is which. For that, we use another right-hand rule. Let me teach it to you real quick here. If you have a current carrying wire, you can find the direction of the magnetic field on each side by taking your thumb. Do it with me as I'm doing it. Take your thumb, put it along the current right now. Put it along the current. And your fingers, pretend you're grabbing that wire right now like this. Your fingers will tell you right now if you're coming out or going into the page on either side of the wire. If you do this correctly right now, you shall see your fingers are pointing toward your face on the left side. And on the right side, if you curl them around, they're gonna dive into the page. I wanna take a moment to make sure everybody sees this. Tell me if you don't see this in the chat, or let me know. Thumb along the current, hug the wire with your 4 fingers. They're gonna be coming out of the page on this side. They're gonna be going into the page as you curl them around that side. Tell me if you don't see it. We'll give you a few seconds. All right, so hopefully that means we are all seeing it. Okay, if not, just let me know. We'll do the same on the problem right now. So we go back here. The direction of the current, yeah, we said the current's going like this. So again, your thumb along the current, wrap your fingers around the wire. You should be seeing right now that on this side, the magnetic field's coming toward your face. And on that side, it's going into the page. Okay. So that's how your rings are oriented. Give yourselves a second to see it as I'm tweaking things here. Now, that's going to continue along the entire segment too, right? Like no matter where you do that right-hand rule, you're going to see that along the entire segment too here. It doesn't matter where you do it right now. Okay. So these again, these 2 symbols belong to a ring. I want to remind you, they belong to a ring. Okay. So here's my question. Hold on. We're going to make this very visual. Here is my question, okay? If I grow this ring, because eventually that's what's going to hit point P. If I grow this ring right now, which direction do you think is going to hit right now point P? Which direction? Into the page or out of the page? I'm growing the ring, right? Which direction do you think is going to hit point P? Into the page or out of the page? When, you know, the ring reaches all the way out to point P. Which one is it of the 2? Which one do you see on the image here getting, you know, to point P, actually?
Out to the page.
Out of the page, okay. So it's the dot. And the dot, Kelly, symbolizes what direction, according to me?
Positive set.
Good. That's me. I did that, right? I mean, I put in what the dot would symbolize in cylindricals. Perfect. So now you know that the magnetic field, okay, the magnetic field at point P is going to point in this direction, or as Kelly said, in the Z right now, positive Z. Perfect. Which means you can use the hack. Why not use the hack right now, right? That we were talking about earlier and show you how that works. So I bring in my Biot Savart law. I have a few things to take care of. I bring in my Biot Savart law, but I already know this. So I'm not going to consider the vector version of the equation. I'm going to consider this. Fair enough. So what is this? Let's see. DL crossed with R hat. And then the magnitude of that. Well, again, I need to find DL sine of theta. But pay close attention. No matter where I am on this segment, these guys are always perpendicular. Look, because one always points in the phi direction, the other one always points in the r. They're always mutually perpendicular. So that theta between them is actually pi over 2. And sine of pi over 2, I very well know that it's just 1. So wow, look at the simplification here. This is just DL right now. And Natalie earlier told me what DL is, B d phi. It's the magnitude of what Natalie told us. It's the magnitude of that. So it's just B d phi. Good stuff. Okay, I like that. So we are putting in our integral right now, mu naught I over 4 pi dl over curly r squared. Now, dl, we said is going to be b d phi. R, we said is just going to be b for that segment. And you can see how this took shape all of a sudden. Kelly, where should I go from in terms of phi? I need to span this angle over here. What is that angle? Where are we going in the integral from and to?
0 to pi over 4.
It looks like pi over 4, but they've given you here the angle that this spans as phi naught.
Oh, so from 0 to pi naught.
Exactly. And so you integrate. You get here, one factor of b cancels. You get here mu naught I over 4 pi b. And then you just get phi naught. That's it. And when you put it all together, of course, the magnetic field is this entire thing, but again, in the direction, positive z hat. So out of the page, like toward your face, basically. Perfect. Okay, so we got through the grunt of it, explaining again the micro details, because this is a complicated law. Okay, but we got through the brunt of it. And now what I want us to do is secure that we know what we're doing by doing the segment 4. This was segment 2. So that's segment 2 right there. I'm going to put it over here. And now we're going to do segment 4 in the exact same fashion. So be prepared. I'm going to rotate questions. Okay. Now, for segment 4, the R vector is going to go now to this DL. Okay. And the unit vector, R hat, is going to point like this. And now my first job is to always write down what R, the vector here, is. Kelly, how big is this R vector throughout this segment here? How big is that? The size of it?
A.
A. And the direction you would say, where is it always pointing as we integrate along here?
Negative R hat.
Good. Now, for DL, let's ask Natalie, again, since she did it before. For DL, What would you say here, Natalie? Is it going to be this time? Same logic, but a different R this time around. If we were to find the size of this, what would you say this is? The size of DL. AD5, good. And where would you say it's pointing? Which of the two, I guess, your component, like directions? Take a look again before you answer that phi points counterclockwise. So if you're going clockwise, think about what that means. So what direction is DL pointing? It is pointing, whoops, it is pointing negative, negative phi. Okay. So let's put that in. We won't need it though. We're going to use our little right-hand rule again. So let's do it with, who probably has easy access to their screen here. I'll do Leah right now. So Leah, I want you to use your right hand again. Here's the current. Hug it. Put your thumb with your right hand again. Your thumb along I. Hug the current right now. Your fingers, answer me this. Is it the left or the right that your fingers point inside the page? It's one of the two. Where do your fingers point inside the page right now if you hug the current? Is it the left or is it the right side? It's one of the two. So again, if you forgot the question, where do your fingers point inside the page, like toward the screen? Is it on the left side or on the right side? Don't worry, Natalie. I'll give you the rest of the recording. Don't worry. But Leah, do you have the answer? Can Kelly help her out?
The left side.
The left side. Okay. So the left side here, it's basically this inverted now because we're going the other way. So the left side here is X, the right side is the dot. Here's our little ring of magnetic field. Obviously, when we grow this ring again, it's going to be the X right now. When we grow this ring, it's going to be the X that hits that point P. And X corresponds to negative Z. So I expect again, before I even do anything, I expect the magnetic field to be pointing in this direction or negative Z hat. So that means I can use the shortcut again. I won't have to be looking for the entire magnetic field. And we talked about how to use the shortcut. We're going to take the magnitude of the cross product instead. And the magnitude of the cross product is again DL sine theta. But again, throughout the motion here, angle between R and DL is 90 throughout the motion of that segment. Sine of 90 is 1. We just need the DL, which Natalie had told us. It was, again, 85. And no, I don't care about the negative. Again, we're taking the magnitude of this, right? So it's going to be just 85. Then I go in, and I'm basically going to put everything right now in my Biot Savart law. I got it all. So I get in total mu naught I over 4 pi, the integral of dl over here over r squared. All right. And then we know that dl is a d phi, r squared is a squared, and everything just falls into place. 1 factor of A cancels. And over here, here's where I want you to be super careful. I'm going to ask Kelly this, but I want you to be super, super careful, Kelly. When I'm looking for the size of the magnetic field, what do I expect to get, a positive or a negative number? Be careful.
Negative.
Am I expecting a negative for a magnitude?
Oh, positive.
Right, it's the magnitude of B, right? So we're considering the size of the B vector. So you know you should be getting a positive, right? Now, where are we going, Kelly, in terms of the angle for the integral? We're going from here to here. What does that mean?
From phi naught to 0.
If I put that in, Kelly, are you sure I'm going to get a positive?
No, so you have to flip it around by multiplying -1.
And this probably will make all of you uncomfortable, right? So why am I taking the integral from 0 to phi naught again? Well, it's because I know that I need to be getting a positive. I cannot actually get a negative for a size. Another way you could do it, if you really want to, you just be taking the absolute value of this whole thing, right? As you're doing the integral from phi naught to 0. You could do that as well, but you could just flip the bounds, right? To make the whole thing positive. So I recommend being extremely cautious and asking yourself, when you do the integral in these problems, am I expecting a positive or a negative? Obviously a positive. B is a magnitude of the magnetic field. So again, either way you want to write it, I'll just flip the bounds for you right now. So as they're going from 0 to phi naught, and that will fix the issue for being positive. And so again, I'm only remaining here with mu naught I over 4 pi a, and then d phi in the bracket here. So my answer is mu naught I phi naught. Okay, and the full magnetic field is this expression again, but in the negative z direction. So what do you think I'm going to do to find the overall magnetic field now? I got the magnetic field contribution of each segment. What should I do to find the overall magnetic field? Bogdan, since I have the magnetic field of each, what could I do?
We just add them.
We add them together. And the directions right now are taking care of the negative signs. So you only have to add these two together, really, to get the overall. Okay. So it's the sum of all the magnetic fields here from 1 to 4, all sides, basically. The ones that were along the R didn't contribute anything. So all I'm adding is these two. So you get here mu naught I. We can factor a little bit. Mu naught I phi naught over 4 pi. And then inside the bracket, we're going to have 1 over B minus 1 over A times a Z hat. And that is our final answer. That is the overall magnetic field. I can make it a little prettier, but I won't. Monster of a problem. You know, when you get into this, of course, it's not going to be very friendly. And yeah, hopefully, again, you followed through. It's not an easy topic. So you're going to get variations of these kinds of segments. I'll show you other variations that you could see from my folder here. I picked this one. You could have seen something like this, okay? Again, you can see the point P and the segments here that they would ask you to do. You can see that you would break this into 3 segments, and this again here into 4 segments, right? And some would contribute, some would not. In A, for example, this would contribute, the straight ones would not, actually. And in part B, the straight ones, again, they would not contribute, while the curved ones would, just like in our problem. So you expect to see variations. Another variation is this one over here, where point P is in the middle of a semicircle wire here, and the top and bottom here extend to infinity. Now, every single one of these actually contributes, and I want to prepare you. Obviously, you can see the segments that you need to break this down. Here's 1, here's 2, and here's 3. You can try this problem on your own and see what you get. It's not going to be as simple. The straight segments here are going to be a little bit more challenging. Because
Actually, I do have a question for this problem. Won't the straight sections that you just showed cancel out?
Actually, no, Bogdan. And that's the interesting thing about this problem. You'd think so, that they would, but they actually add. And the reason is, you can see here, we get X from the bottom side that's going to hit point P when we do our right-hand rule. We also get an X over here from the top part. It's going to hit point P. They actually add, surprisingly.
I have a question.
Yes.
So like, they will contribute if they're into the page or outside a page that is like touching point P.
Kelly, the quickest way to tell is by the cross product. You look at the cross product, right? And if you have you have DL and R, again, being parallel or anti-parallel, you know they're not going to contribute. But in this problem, for example, that you're looking at, for the bottom segment, for this segment over here, here's DL, here's R. They're not either parallel or anti-parallel. They're somewhere in between. Like there's a segment here of R that's parallel to DL, but there's also a component of R that is perpendicular to DL. So there's going to be contribution.
Okay.
However, in our problem, DL here and R were always parallel, as you can see here. They were always parallel, pointing in the same direction. So their cross product is always 0 throughout segment 4.
So you look at the cross product.
Yes, between the two here. Okay. Okay. So the next one I want to do invites you to calculate the current as well. Again, for the sake of time, I'm prioritizing. I want us to do not this problem, but rather the ring problem first, because these are very challenging again. If you get this, we might have the time to go through either the cylinder or the sphere problem if you haven't died on me yet, because it's going to be pretty interesting. What do they say here? They give you a ring. So a ring, not a disc, and it has charge Q on it, radius R, okay? And we're going to make this ring spin. Going to give it some angular velocity, omega. Okay. My first job here, before I even do the problem, I'm doing magnetism and I'm using charge. No, I can't do that. I need to find current. This is going to be a common thing for you. You need to find the current here. Before I do that, can I ask Kelly over here, what dimension is a ring? 1, 2, or 3 dimensions if it's an infinitely thin ring?
1 dimension.
So it's best described by lambda, sigma, or rho?
Lambda.
Lambda. Do you think you could get me what lambda is here?
Q over R.
close.
Oh,
Okay.
wait,
So the Q is spread.
omega.
Hold on, Kelly. The Q is spread around the circumference of that ring.
Oh, 2 pi r.
Yeah, that's your lambda. Okay, so how do we get the current? We know right now, if I take one little element here, dl, this dl is spinning right now at this velocity. Yes, it will contain some charge in it. Okay, this dl that we're drawing in the diagram, it will contain some charge called dq. Fair enough. How do we find the current? I would start by looking at the definition of the current. So definition of the current said it's the change of charge per unit time. Okay, but Kelly again, because I know Kelly knows how to do this pretty well. Kelly, how would you describe dq right now in terms of lambda and dl? Just like you did for electric field when we're doing that chapter.
Lambda times dl.
Mm-hmm. Okay. And can I ask Bogdan, what is dl here? Like the size specifically of dl, since we are, we're in a ring situation. What do you think, again, the size of dl would be, Bogdan?
Yeah, isn't it dq over something? I think r. Oh no, the dq over the phi.
I'm looking more about the arc length formula over here. So dl in terms of these two.
Okay, so it would be the dq over r, or no, d phi over r.
Times r. Times r. Yep. Perfect. All right, so we know how big dl is. Here's our definition of the current. And now I'm just going to walk in and start plugging things. So dq, Kelly said it's lambda dl, and we're dividing by dt. And then we said that dl is r d phi, and we're dividing still by dt. I don't know if you noticed this, but look what I'm getting here. Can Leah tell me, is Leah still here? Yes. Okay. Can Leah tell me, what do you think this d phi dt represents here? This change of angle per unit time. So it's somewhere on the diagram. What is this guy? Because I can do this. I can move the partials around, and I can write the derivative like this. What is this derivative, actually? First of all, I want to make sure that Leah can hear me. Can you hear me, first of all? I haven't seen a message from Leah in a little while. But if you can hear me, let me know in chat so I can direct questions to you. But if not, right now, I'm recording this, so it doesn't really, it's not really going to ruin everything if you can't hear me. But Kelly, what should this be?
Omega.
Yep. So we put in omega. Now I'm going to do what Kelly told me for lambda. She said do q over 2 pi r. So we're multiplying these together. Okay. You get rid of the r, and there's your current. Q times omega over 2 pi. Let me pause one sec, because I think Leah's trying to reconnect. 1 second. Awesome, we're all back. So we got here our current, and what I did was, again, I expressed dq, I opened it up as lambda dl. Kelly had found what lambda is, right? And Bogdan what dl is. We plugged in dl, and then I noticed that I'm getting here d phi dt, which is just omega. And then I collapsed that to omega, put in the actual lambda right below, did a sort of rearrangement and got my current. Done and done. All right, so now that I have the current, finally I can go and do the problem. This is going to be one of those problems that has symmetry, which means we're going to use the shortcut again for the Biot Savart law. In fact, I haven't shown you one where we don't use the shortcut. I wish I had the time to do the one here, right above it. That's the one where we actually cannot use the shortcut. But anyways, for the ring, I feel the ring is more of a priority to be seen. You're looking for the magnetic field at a point P along the symmetry axis of the ring, so along the Z axis here. Okay. You probably can sense some kind of symmetry here, and you'd be right. If I pick here, let's say right now, I want to make this realistic. If we pick here that this ring rotates, let's say this way, that means DL will look like this right now on the top part, and it will look like this on the bottom part, right? I pick two segments again, DL on the top and bottom, that's how they will look like. And then my immediate move here is to draw the R vectors. So there they go, launch toward point P. As we said, they always point toward the point of interest from the element. So there they go. All right. So when they arrive at point P, we need to think again where the magnetic field is going to point, which is not obvious right now, is it? DL up there. I think I'm misleading you right now with the way I've drawn DL. I really think I'm misleading you. Think about this for a second. This is a false 3D diagram. And being false 3D, as the name suggests, I'm probably screwing you up to see the geometry here. In fact, the ring right now, from your perspective, would appear like a straight line, like that thin, because you're looking at the ring, you're looking at it like this, right? Like straight on, like this. So you don't get to see the backside. I've shown you a false 3D diagram, which looks like kind of like this right now. You don't get to see the backside over here, okay? You only get to see a straight line when you look at it directly ahead. What does this mean? Well, for the DLs, if the current was going like this right now, when it reaches the top over here, it's actually either going into the page or out of the page. Not the silly way I drew it. In this case, if this is omega at the top, DL would be pointing toward your face. The DL would be like coming out now from the back. And then in the bottom, it would be dipping into the page. Interesting. Okay, so none of this silly business with the arrows there. So these are my DLs. Okay. Again, I'm spinning in this direction. Fair enough. Okay, so I put my R vectors in already.
Wait, sorry, how do you see it? It's into the page and out to the page.
I imagine myself being on the ring right now. This is still kind of a false 3D diagram because you can still see the backside. The backside being this here, Kelly. That's the backside. If I'm spinning like this, it means right now I'm moving like this, right? Like the current's going like this. And then here, it's going to dip into the page. and then come out the back going up,
Oh, okay.
right? And when it reaches the top there, for a very brief moment, it's going to go outside the page and now continue going down like this again. That's what's happening right now. Obviously, if I change the direction here of the spin, these are going to flip, right? These are going to go opposite. Fair enough. So now what? Okay, here's the super cool part about this. I love explaining this. I will tell you that DL and R define a plane. You might not believe me, but they do, okay? They are two vectors right now that are literally, you can use from Math 115. Just recall from Math 115. If you had two vectors, look, you had like V1 and V2. As long as they weren't parallel, they could be used to define a plane, right? And we know the equation of a plane has a point plus two, again, linear combinations here. Again, C1, V1, C2, V2. That's how you wrote the equation of a plane. I'm just reminding you. So as long as you have two vectors that are not parallel, you got a plane in your hands. Bear with me. How would the plane look like here that you would be defining? Use your creativity here a little bit, because again, this is like very visual. DL is pointing out of the page right now. So I got a vector, it's pointing out of the page, and I got another one. So here, I'm going to do it on my perspective. I wish I could do it in your perspective, but it's still going to be mirrored. So I got DL pointing out of the page right now like this. And I got R pointing like this. Can you see the plane? Can you see the plane here? I just want to show you again what the plane looks like. Here it is. You see, it slices. It goes out of the page toward your face and into the page. It's a square right now that slices your screen, and it goes into and out of your screen right now like this. Think about it for a second, because it's important to see that. You barely can see this pen, but again, DL points toward my face. R goes like this. You can see the plane, right? Look at my video. You can see the plane right now. So the magnetic field is perpendicular to that plane, because you're taking the cross product between these two vectors. That's what's going to give you the B field. It's always perpendicular to that plane, defined by DL and R. Amazing. So in our case, you put your thumb along DL. You don't need right now the plane. You can do it on the screen. Put your thumb along DL. This is going to hurt a little bit. Put your index finger along R, and you'll get the direction for B. I'm going to give you a few options, and you will select the one that's correct, okay? Let's see if you get it. We're doing the top one right now. Here's one option. Here's the other option over here. Hold on. Let me make sure I do this correctly myself. Like so. Okay. Ignore this for now. Ignore that. Which is the correct magnetic field? The top one or the bottom one after you do your right-hand rule?
Top one.
Top one. And we can see that if I need to be super careful here, that's a 90-degree angle, okay? Perfect. Again, you can see the plane, again, slicing, the DL and R slicing again into the page, slanted plane right now. And there's your magnetic field. Okay. So from the bottom one, we do the same thing, right? And now we have the DL pointing into the page. You're going to start with your thumb pointing into the page. Then your index is going to follow the R vector. And now you're going to get a B field that points down into the right. It's going to look like this. And I want to make sure I convey this. R and B are always perpendicular, right? We're doing a cross product to get B. So this is another perpendicular arrow to R. I think you can see the symmetry now, right? I think you can see it. So BZ is what survives, okay? So BZ here is what survives. And any planar component right now will die. Okay, these will die away. Interesting. So BZ is what survives, and I want to find what BZ is in terms of B, just like I did back when I was doing electric field. You know, I want to do the same thing here. Leah, do you think you can help me by using this angle here? I'm going to call it theta. Use these two to get BZ right now. What do you think? I hope you can still hear me. Okay, maybe not. Bogdan, do you think you can get me this in terms of the other two?
Yeah, shouldn't it be B arrow over BXY?
We're not going to use this guy, right? So we want this one, the surviving component, in terms of the big B and the theta. Just like you break down components of vectors. It's either a sine or a cosine component.
Oh, it's cosine.
Okay. So it's B cosine theta. And B again, where am I going to get it from? I'm going to get it from the Biot Savart law. From the shortcut of the Biot Savart law. Okay. Now, I need some more things here before I move on. So, okay, I got what B is. I see cos theta. I'd love to know what cos theta actually is. Leah, you got it as well. Sorry again, I should have waited a little bit longer. All righty. So, Kelly, I want you here. And let me ask you something. How could I move this into the triangle from here? Can I say this? Maybe, I don't know. Are these something special?
Yeah. Yeah.
What are they?
Cojacent angle.
Opposites? Are they opposites?
I don't know.
Well, they're not, okay? And it's a very common mistake that I've done in the past too, to assume that they are. They are not. And I've tried my best here to show you the offset again. They're not opposite. You can't call this theta or that theta. In fact, you can do something else. Kelly again. What's the total angle here? Like if I go and circle this, what's the total?
180.
180. Then what should this be?
9 180 minus theta minus the P angle.
90 degrees, right?
Mm-hmm.
Perfect. So you see what I remain with? 90 minus theta. That's actually what it is. This guy here is 90 minus theta, and so is this guy for the same reasons. And because I have a right angle triangle here, that makes these top guys here theta. Problem solved. Okay, fair enough. Now, the ring had a certain radius that I'm ignoring here all this time. It had a radius R, capital R. So I think you can start seeing where I'm going with this. I will also call this distance here from the ring to point P, I will call it Z, obviously, because we're going to set the coordinate origin on the ring. Why wouldn't we? So I'll call this Z right now. Presumably, again, this would be like the Y, and this can be like the X direction right there. But we're not including these in the diagram. I'm just showing you where the origin would be. Okay. So what is cos of theta really? Well, again, it depends on you right now if you want to work this integral in terms of, if you want to work this geometry, I guess, here in terms of cos theta or not. It's up to you to choose. However, just know that the integral itself is not going to depend on theta. You'll see. Because that angle theta, it's not going to change. How do I know that? Okay. I need another demonstration here. Here's the ring that you're integrating right now, the charged ring, okay? And let's pretend the camera is point P. This is going to be R right now, my pen. I just want you to see something. As I integrate around, the amount that I'm bending, again, with respect to the ring doesn't change. As I integrate around, that theta angle between, again, pen and ring stays the same. And in fact, if I see it from this perspective, let's say point P is here right now, where my fingers are, like where I'm snapping my fingers. Take a look again, that as I integrate around, the angle between the R vector and my ring stays always at 90. You might not be seeing that. So let me show you again a false 3D diagram. Here's point P, okay? Say you consider right now this DL right there, okay? The R vector would look like this. You'll say, I don't see that being 90 degrees, you lied to me. It actually is. Let me explain. DL is on a plane right now defined by the ring, and R is off that plane. The angle between them is 90. And I can build more DLs to convince you that this is a thing that doesn't change. You can think of this as a party cone hand, like a party cone, the birthday cones, birthday party cones that you wear. That's the geometry that you have here. This is always 90, no matter where you take this from on that cone, okay? That's always going to remain 90. Any DL that you consider on that ring, 90 again over here. So what am I suggesting? I am suggesting here, oops, sorry about that. I am suggesting here that the angle between DL and R is always 90. When I do this cross product and I dumb it down to DL sine theta, I should be careful not to call the two thetas the same thing. Let's call this sine phi. The angle right now, okay, always is 90 throughout the integration. So again, this dumbs down to 1, and my cross product gets me DL back. Beautiful. So that's the geometry that you have between DL and R. Now, I need DL. I think Bogdan, though, got it for me earlier. RD phi. I have that. I mean, might as well rewrite it down here if you want to. Perfect. I also need my current, right? And we got it together here. So I'll copy the result again. I need this current. I've not been given it in the question, so I need to use omega, right? Not omega and Q, not I. Perfect. What else am I missing? What's cos theta? Can we see what cos theta is? Bogdan, I want you to take over here and take a look at what cos theta is right now in this triangle. What is cos theta in terms of sides?
Yeah, that'll be R over R arrow.
Over the curly R. Okay, and while we're still at it, could you tell us what curly R is itself right now? Because this is a right angled triangle. Can you use the other two sides to tell us what this is?
Yeah, it's square root of R squared plus Z squared.
Absolutely. So I think you see where I'm going with this, okay? I'll put these again, maybe on the left here. I don't know, actually, maybe on the right, just to have all the tools here. Perfect, and then you got what the cross product is as well. That's it. You literally now can solve the problem. So again, this is the guy that we're gonna plug everything into, okay? Whatever you see here is gonna go into that top equation from symmetry. So let's start. Okay, so B again, you said is gonna be this integral from the Biot Savart law, and we're gonna multiply it by cos theta. That's exactly what we're gonna be doing right now. Sorry, again, my pen is a little unresponsive. And by a little, I mean a lot. Right now, we're not registering the pen on the screen. Give me a second here. Okay, I guess we're restarting. Gotta love online sessions. You gotta love them. All right, let's see. Can we register now? Let me pause the recording one sec because it's not working. All right. So we got here B, right? We said this is going to be our B. We're multiplying this by cos theta. This is supposed to be our BZ. Okay. So again, I'm going to start substituting. For the current, I got that it is equal to Q omega over 2 pi. And then for the integral here, the size of this, we found out to be only DL. Now, cos of theta, we found out to be, from Bogdan, you can see it down here, capital R over curly R. Okay, so we got in total here mu naught Q omega over 2 pi. We're going to pull outside the capital R as well to the front. We're going to end up with DL over R cubed right now. And you already have told me what these two things are. So again, focusing only on the integral for now, DL is R d phi from our findings. And R cubed, Bogdan got us what R is. So R cubed is going to be R squared plus Z squared, square rooted, but raised to the power of 3 at the same time. So that's how our integral is looking like. However, notice that the integral is literally in terms of phi. So anything that is not phi related can be pulled outside right now. So in total, you have mu naught q omega r squared over 2 pi, and this thing here raised to the 3/2 power. And then you're only working out the integral. And I want Kelly here to tell me what the bound should be for this integral. If we're doing the ring, how much should we go around phi? What was that, Kelly?
From negative pi over 2 to pi over 2.
Right, or we can think about it as, again, spanning here this whole thing, which is going from 0 again to,
Pi.
yeah. Okay, from 0 to 2 pi. So basically you cancel this guy and you get what your magnetic field strength is going to be. For the direction, we know it's going to be in the z hat. We did the symmetry. And so our overall result is mu naught q omega r squared over that weird square root thing on the bottom. And that's it. That's the magnetic field of the ring. Okay, so the integral was pretty fast. It was just phi dependent, so we didn't really have to integrate anything. Everything else got pulled outside, right? So it should give you some vibes from the electric field chapter. However, it's not the electric field chapter, right? It's not a charge ring finding the electric field. It's the magnetic field, different geometry, cross products involved, etc. Okay. Now, do you have the energy for one more? And particularly, I wanted to look at either the cylinder or the sphere that's spinning here, a spinning cylinder or a spinning sphere. Do you have the energy to see these, one of these as well? You can do the other one if you see the first one. You can take a vote right now.
Yeah, mother or.
Okay, Kelly and Leah, same feelings? We want to just see one of them? Kelly?
Either of them is fine.
Okay. If I was to pick, probably the harder one is the sphere, I'd say, to see. And then the cylinder, you can easily break it into rings as well. So I'd probably go with the sphere one for now and show you. I want to make sure, first of all, that I got the result right for the spinning ring before I even jump in there. Right? We don't want to get that wrong. Okay. I forgot the 4 pi here. Hold on. See, that's what I mean. Like, we got to be a little bit careful because there was a 4 pi here that got pulled outside and it was just chilling there. We forgot about this as we were putting in the current. And so, you know, you got to be a little more careful. Okay, so 8 pi squared. All right, and if you cancel that, you remain with a 4 pi. Okay, so that's good. Just making sure again. So I'll just to be safe, I'll copy the result from here. It looks a lot cleaner. It's exactly the same, honestly. And I'll go and use this as a building block right now for the problem that we're going to do. We're going to do the sphere. So this is for a ring, right? And I've taught you that you can use previous results to derive new ones. So for the sphere over here, let's see how this will play out. We have a sphere of radius r, okay? And it's spinning again about an axis So I'm going to put the axis, doesn't matter where you actually pin it. I'm going to put the axis right there maybe. Okay, and it's spinning about this axis at angular velocity omega. Fair enough. Now, it also carries uniform surface charge density sigma. And we want to find the magnetic field at its center right now. This is the point of interest, right at the dead center. How do I do this? Well, I can use a building block over here from the ring result. I can break the sphere into small rings. Here's one of them, for example. And that ring is going to have not a radius capital R, but rather some other radius here, little r. We've seen this geometry though before. So that's little r, okay? And we can think of that being Z over here. So from the center of the coordinate system here for the sphere, you can think about this being a Z. Okay, so you got Z and little r up there. There's our capital R. Fair enough. And then we're thinking to ourselves, what's the current that this would contribute? It's obviously not the current that the entire sphere would generate, right? I want to find what the current of this little ring will be. That's my goal right now. How can I get this DI? And so I think of it the same way as I did for, let's say, the ring earlier. I go, okay, everybody on the sphere right now will rotate at speed omega. Rotational speed for an extended object is a shared property for all the points. So like if I spin a rock right here, like this, every point on that rock is spinning at angular velocity omega. But if I pick points on it and ask about the linear velocity, every point will have a different linear velocity based on how far it is from the center of rotation. But omega is a shared property across the entire object. So this ring is also spinning at omega. Just keep that in mind. Okay, so then this reduces to me finding the current of a ring. I've done this exercise before, but I'll do it again. Here's the ring, okay? Spinning again at angular velocity omega. We did this earlier. We were saying that the current will be dq over dt. Then you ask yourself, what is exactly dq right now? Remember how I told you that when you're doing this kind of approach, you're thinking of the building block here being smeared across the surface? Remember how I told you, like, yeah, we'll use the ring, the result of it, but we're gonna ever so slightly smear it across the surface so that we create a little area. In fact, that's what I'm going to do here. That's what I'm doing. I'm smearing this little ring right now that we're using, smearing it across the surface of the sphere. And it creates a little area if we do that. The little r is the average radius of these two rings that I've drawn over here. It's the average. But again, these rings are so close together that for our purposes, they can be considered a single ring. However, now I've actually created some surface area here. And if I open this up right now, if I open it up, I take a pair of scissors and cut it. We'll come back to this in a second. So if I take a pair of scissors and cut this little rubber band, remember the rubber band technique? I get here a rectangle, and that rectangle has a size here, ds, and then the circumference of those rings, so 2 pi r. Okay, so that's what we have. And if we want to find the area, that little area right now, it's of course the product of 2 pi r and ds. What is ds? Right, because it sits over here. I'll remind you, we've seen this in the past. Again, if you draw a couple of lines from the origin to ds, you can see what ds is. Each of these lines, because it touches the surface and it travels all the way to the center, is capital R. We can use the arc length formula again. This is capital R. And this little angle that I'm opening up is a very small change in polar angle. This being the polar angle itself. Right here. So it's a very small change in polar angle. Okay, so ds again is r d theta. All right. Now, sigma has been given, okay? Sigma has been given. We can just use that. Otherwise, if we were given charge, we could divide the charge by the surface area of the sphere to get sigma. But sigma has been given. So coming back now to here, okay, I want to find the current again of this little, not cylinder quite. For our purposes here, we consider that to be a ring. So sometimes, again, you consider this shape to be a ring. Sometimes you consider it to be a little cylinder. I'm selecting the top ring, but OneNote is selecting the bottom ring. Oh my God. All right. So for our purposes, this thing here is a little ring, right? Because it's squeezed together ever so tightly. Okay, so how do I do this? How do I find the current, right, that this generates right now, this little DI? Well, again, I use the definition of the current, and then my DQ. Kelly, can you help me out a little bit? I want DQ. I have a surface charge density and a little area element right now. How could I get DQ? How could I get DQ in terms of sigma and dA?
You multiply it.
Multiply them. Perfect. So I'm going to go here, do the same thing. Sigma, dA. Fair enough. So when I go through with this, okay, I eventually can open this up. Sigma here being sigma, but dA is 2 pi r, and then ds over dt. Now, one thing I should be careful though about, okay, one thing I should really be careful about. When I'm doing this right now, I have to be careful about the ring itself. This is a little bit tricky, okay, because it belongs to a rotating sphere. So when I open the DQ up, yes, sigma dA is fine to write right now for DQ, but it's going to be harder for you to dig out what the relationship is where I can shove in omega right now. That's what I'm talking about. Where am I going to shove in omega over here? So that's what I mean. It's a little bit harder if you use this formula here. I'm thinking of a way to show it to you so that it's like bright as day where omega is going to go. Okay. I think you can see it over here. Not if I plug in ds, but rather if I truly consider this to be a ring. So instead of doing sigma dA, I would do lambda dL again. So I'll pretend that this ring has a linear charge density, and dL is going to be, of course, the total length of it over here. If I do that, I basically end up with, if I'm trying to find what dL is on this little ring, let's say here, what is this little dL? That is going to be, again, I don't know if you can see it well, but I'll zoom in a little bit. I want to find the size of that dL. It's going to be r d phi. Because that little angle in there is going to be d phi. So I have r d phi here yet again. I don't know what lambda is. Lambda is an unknown for now, but we'll get to that in a second. And then I have dt on the bottom. Then I can do this like I did for the ring earlier. And you can see now that this is just omega. So your answer here is lambda r omega is going to be your little current from the ring. But I don't know what this is. However, I remember from the electric field chapter that lambda is related to sigma. How? They were related by a multiplication, if you remember. This was the multiplication. This might ring a bell, okay? It was from back in the day where I was proving to you. I might have it over here, but it's going to be hard to dig out. I was proving to you how these are connected back in some other problems earlier in the term. I think we were doing electric field for those. But we've done the exercise. It's just been a little while that we've seen it, for sure. It's not recent. Probably in the electric field stuff. So I know that I've done this somewhere over here. You can search it up to prove. It's very simple to prove that this is true. So we can use the connection between these two. So that lambda is sigma times the stretch, the smear amount. That's how much I've smeared this right now. Okay. So this is fair enough. And so when I get here, if I want to involve sigma, right, what I need to do is be really careful about that smearing amount. Okay. I got here sigma r omega ds. I know what ds is. We've proved it to be r d theta. Okay, we have to be, again, very, very careful about what that current is. Okay, fair enough. You have to be somewhere, Leah. Don't worry about it again. Do watch the rest of the recording for the problem. I might speed it up a little bit now so we finish within a decent time. So once I get the current, okay, which is the difficult aspect here. Once I get the current of the building block, all I have to do is fill in this. Okay. So once more, if I want to use what the result was for the ring, these R's and Z's change. They're not going to be capital R and Z naught. We're going to vary these now. So this guy's going to be like little r. This guy's going to be, again, over here, a variable. And we're going to have to integrate the entire function. So for the sake of time, here's what I'm going to do. I'm just going to walk you through very fast on what happens, okay? For the sake of time, because I noticed it's like already 6:10. I don't want you guys to leave on me I just want to show you again how you would deal with it. Not this problem, but this one over here. Okay. See, again, same geometry, but the difficult part about this was to get the current of the building block. How much current is it providing you with right now? You can see I got it again like this, with dq being lambda dl, okay? Plugged in the connection after what lambda is in terms of sigma. But I left it like this for a little while in this answer. I left dq unchanged until it got to the integral part, of course. So this is what the little current is of each ring that I use on that sphere. So once I establish that really quickly, I want you to see the setup again. Here's my smeared rubber band, okay? The current that it provides, the radius of that rubber band, the smearing amount. I use this for the arc length formula, the RD theta part, to get what ds is. That's all I did. And you can see basically a repetition of the setup that we had for electric field. I snipped the rubber band. I showed you this part in our solution. We derived what ds is, that it's equal to RD theta in our solution as well. These are some more relationships here that you've seen before, right? Between R, Z, and the polar angle. Nothing complicated. So you can see that they make sense here. If you wanted to express this guy in terms of these two, it's obviously here on opposite side. So it's going to be a sine relationship. Little r is going to be r sine theta. Similarly for z, since it's an adjacent side to theta, it's going to be a cosine relationship. So r cos theta. That's where these come from. dq, like Kelly said, is going to be sigma dA. We know what dA is right now. It's the product of these guys. So I put it all in basically here. I plugged in what dA is to go to the next step. Okay, so it looks so far like this has become an integral of theta. And I will work in the theta world. It's easiest. Here is the formula for the field on the axis of a ring. For our purposes, this guy is now an infinitesimal because it's not the entire sphere. A ring makes up a portion of the sphere. This guy has become little r because, again, the radii of the rings change as you integrate around the sphere, right? They change. And z here, well, has been left as z. So you'll see those changes being done here, okay? Again, as I mentioned. Okay. If right now I could write down what this is, and what this is in terms of theta, I'm ready to integrate. I've already done what r is in terms of theta. It was r cos theta, or r sine theta rather. That's what this is. I've already done the r guy, and I've done the z guy too. Z was r cos theta. You see what I'm saying? So the remainder is the di. Remember di used to be omega over 2 pi times that dq, which I hadn't changed yet into what it is. I'm going to change it now. It's going to be sigma times dA. You're going to see that happen. It has happened here. So we followed through. I put in what dA is. And then we just basically opened it up all the way. So now we put in this version for dq. The whole thing, as you see it, we just shove it in there. And you've got your integral in the next step. It's going to be a theta integral. So you have here sine cubed d theta. Everything else is constant. Where are you going to take the integral from in 2? Kelly, if you want to cover the entire sphere, where are you going to rotate this vector from in 2 in terms of theta?
From 0 to pi over 2.
Pi over 2 would rotate it all the way to here. We want it to
Pi.
end up, exactly. We go from 0 to pi. That's what you'll see me do here. So it's just the integral of sine cubed d theta. I've taught some tricks on how to deal with these using the Pythagorean identity. Basically, when I see this, I'd like to break it into a sine times cos term. And that's what I do here. If I replace this one with 1 minus cos squared times sine theta, I can distribute this in here. The first one is going to be super easy. It's just the integral of sine theta. And the second one is a product of these two, as you see here. The antiderivative of this, super easy. We have a rule. It's going to be cos cubed over 3. You can try and see if I'm being real, because if you differentiate this, you get 3 cos squared theta sine theta divided by 3. So you get back the original that you have in the integral. We have a rule for these. Okay. So then you end up with your antiderivative here for each one, evaluated from 0 to pi, and then you get to your answer down here as you do the algebra. It's a very simple answer. But it's a long problem, right? And to write everything down would probably go to 630 plus. So I just wanted to show you the gist of it. Use the ring as a building block, smear it across the surface of the sphere, and ponder upon what the current is going to be of that smeared ring. But this is the difficult part I feel in this problem right now. Okay, so I took the ring, took a small dq on it, and I asked, well, how much current is that providing as it's spinning around here? Like this dq is moving around this ring at a speed omega. How much current is that generating? That's what I asked. Okay. So I did it here in a little bit of an interesting way. You don't have to do this way. You can do the way that I showed you in our solution, and it will work just as well. However, I think this part, we should come back in the next session and talk a little bit more about it, because it pops up in other problems as well. You'll need to calculate the current of spinning things. And I want to get a little bit more precise with how you should be doing it. So for the sphere again, use the ring. See again how you can write dq over dt and write the dq in a clever way so that you can involve omega in it. That's the goal. That's the whole purpose. How can I write dq in a clever way so that I can involve the spinning velocity in there? And that's about it. So I'll give you both solutions. I'll give you this solution to have for the sphere. But for the time being, we'll have to call it here because we've been going for a while and I know you guys want to go. And next time, again, we want to get a little bit more details on how to do this in general as you walk into Ampere's law. There's more problems to look at, but I'm going to look at these before your final. You got the gist of what the whole thing is about today, about what the Biot Savart law is. Okay, so I'll stop the recording here and we'll have something to provide the others with.